Okay, so I've just finished the solutions to this paper and the file got corrupted, so I've got a choice of doing the whole thing again or just doing a quick commentary, and I've gone for the latter given the fact that S2 is coming up in a few weeks. So here's the solutions quickly run through. The first question is a straight normal distribution question that you could get on S1. We can use the tables. It says that there's these rods that with unknown mean, but the key information is that 200, there needs to be a 5% chance that they're less than 200, so I've drawn that in a diagram there. And then when we've done that, when we look at that, we use the Z transformation, but bear in mind the Z number is going to be negative, so if you look in the tables you'll find that number. If you look on the backwards tables under 0.05, I think, on the backward tables, and you find 1.64449. So you use symmetry around the 0 that we get minus 1.6449 there, and we then get this solution, which leads to 200.3. Okay, moving on to the second part. Well, that's just a straightforward binomial. On top of a normal. It says 8 of these rods, there's 8 of these rods where there's a 5% chance of them being less than 200, so it's 0.05. We're asked for the probability that there's at least 3, which is more than or equal to 3, which if you're careful, I drew this diagram when we did it to show that you need to be careful when swapping inequalities and doing 1 minus. And this number we get from the tables as well. Coming to 0.9942, which comes to 0.0058. Okay, and then with the next question, it was a binomial, a Poisson approximation for binomial. We know it should be Poisson because P is very small and N is quite large. NP is 3, so the tables can be used. So important that we appreciate there's no continuity correction here for this question, because we're doing a discrete onto a discrete. Okay, so that's question 1. Question 2 is long and repetitive, I found when we did it. It's a PDF and it's an unknown value of k, and we integrate between the limits here 10 to 2 to find the value of k, so it's straight integration, quite a lot of bits to do, but we integrate the function, use the fact that it's equal to 1, and then we get the required answer of k is equal to 3 over 256. Write down the value of ES. When some of my students did this, they started working out using the formula. There really is no need for that, because this is a quadratic function. It's an upside down quadratic function because of the negative s. And because it goes as zeros on s is equal to, or roots, and when s is equal to 2 and s equals to 10, which are the end values, the quadratic looks like that, which means that by symmetry ES is equal to 6. Unfortunately, though, we do need to use the formula for the var formula, and it's a little bit tedious. You've got to multiply by s squared, because you're finding e of s squared. We already know that the mean, which is 6, but we've got to do quite a bit of work, and it's very similar to what you do there. Obviously, that all the powers are 2 greater, so you're not going to get the same numbers. And we now know that k is 3 over 256 from before, and we put in 10 and 2. The other thing I was trying to emphasize when I made the original video, which you'll never see, no one ever will, is that I tend to like when there's lots of complicated things, not complicated, but fiddly fractions and things. I sometimes integrate, each term around there. So, in other words, instead of working them all out when it's 10 and all out when it's 2, I often find it quicker to do basically 3256 minus 1/5 s to the 5 10 to 2 plus 3 s to the 4 10 to 2 minus 20 over 3 s cubed turned to 2, remembering that they all have to be times by 3 over 256, and which is basically what I did there, and I did the same up the top here. So the answer to that is 196 over 5. However, then we put that into the standard deviation formula and get 16 over 5, because it's that ES squared take away the mean squared. It's asked for standard deviation, so we need the square root of that. And looking at the original question, because it talks about thousands of pounds, we really need to make sure that we write in context here, because it talks about weekly sales. That wasn't a problem here because it talked about ES, and ES is a theoretical function. It's the mean of this function here, so no context is required here. It's just that in this question there is a context. It talks about weekly sales, and S represents thousands of pounds, so we need to times that value by 1,000. I don't think they expected the pound sign, but we certainly need units. We need the units to be converted. I would put the pound sign on as well. Okay, and then question D, again a little bit repetitive. It was to work out the weekly sales exceed 7,100. Well, if they exceed, because they can't be more than 10,000 anyway, more than 10, we're integrating the PDF between 10 and 7.1. I did find, as I say, this question quite repetitive. Okay, question E. Right, now this is a little bit unusual. It talked about a quarter is defined as 12 consecutive weeks. A discrete random variable X is a number of weeks a quarter in which the weekly sales exceed 7,100. So we've got kind of a binomial. But what it wants is the probability. It's kind of set up this other function really, saying that if there's only 5 times when they exceed, or fewer than 5 times when they exceed or equal to 5 times, then no bonus is earned. If there's exactly 6 times when the sales exceed that much, £1,000 is earned. And if there's greater than or equal to 7, £5,000 is earned. So what we do is we will use, and again I use the tables, that number you can get from Px is less than or equal to 5 on the binomial. So y I've defined as basically the same as y is basically these numbers here, with probabilities which are associated with these. So the probability that x is less than or equal to 5 is 0.08822. This I got by using the tables, basically finding the difference between 2 tables. And then looking at this, we had the probability of 5,000 is x is greater than or equal to 7 as 1 minus px is less than or equal to 6, and we can look at that number in the tables as 0.96 something I think, and 1 minus that comes to that. And then the expected winnings is this times this times this, plus this times this. So a little bit of a fiddly, well it's not fiddly, but we had to think way through that question quite a bit, and the final answer is £272.20. Okay, so I think that was that for question 2. Okay, question 3 is again a pretty straightforward Poisson distribution question. We've got Poisson 8 because it talks about the weekly demand for a certain type of camera, and it says a shop has 9 of them in stock. What's the probability of running out? Well, if it runs out, it needs to be greater than 9, which means that greater than or equal to 10, which is 1 minus probability of x is less than or equal to 9. And again, I got this number from the tables, which gives me that. Right, now question B, it says find the expected number of weeks that the shop will not be able to meet on the demand for bird scope cameras if we've got 50 weeks. Well, now we've got a binomial of 50 with this number here. So So we're using the mean of that, which is NP, which is 50 times that, which comes to this number here, which actually seems to have been rubbed out a bit. 50 times 0.2834. Yeah, that's 14.17. Right, part C, for me it's the most confusing question on the whole paper, and there's quite a few fiddly things on this. It says, find the number of birdscape cameras the shop should stock at the beginning of each week if it wants the estimated number in the year in which a demand cannot be met to be less than 2. So wordy. I do sympathise. It took a while to get our heads around this. It's almost worth just trying to figure out what's going on. Let's imagine, for example, that the shop only stocked 9 of them. Well, the expected number then would be 14, so 9 is nowhere near enough cameras so that we would expect there to be less than 2, if that makes sense. So we're looking for some number more than 9. We're using the mean of the binomial originally. That's NP equals 2, so 50p equals 2. So the probability needs to be less than 4%, okay, or 0.04. So then we go back to the original Poisson, because that's how many per week. That's how they're distributed. It's Poisson, and we want, assuming that every week is Poisson distributed with mean 8, we want the probability that the number in any particular week exceeds n, to be less than 0.404. But the important thing is we want the smallest value of n for which is the case. So, for example, it's no good saying n is 50 would be good enough, because 50 cameras, yeah, that's bound to be enough so that there's a very low probability of exceeding that. But we want the smallest number so that the probability is still that low for to run out of stock. So I looked at this number from the tables. Okay, so once I've written this down, I've looked at this number in the tables. This was the first one where the number went above 0.96, which is 1 minus 0.04. So that's why I wrote that number down in particular. And then basically what I did is played with it to get to this inequality. So, not literally, but you know what I mean. 1 minus p, x is greater than 13, is 0.9654. I've kept it a strict inequality so I can compare it with the strict inequality here, which gives me px is greater than 13 is 0.0342, n is 13. Don't worry, there's 2 marks on that question. There's a lot to think about, and in the actual exam not many people managed to do that, so please don't get stressed by that. It was quite difficult. Now, the next part, now this is an approximation question, and it's pretty, but it's also a significance test question. I think it's the only one with a significance test. So in this paper, it's we've got a Poisson 80 because we're talking about 10 weeks. So if every week it's this Poisson 8, then times by 10, we're looking at a Poisson 80. But I tend to prefer to refer in my hypothesis to the original value, the original average rate per week. But it wouldn't be wrong to write 80 or greater than 80 there. Because the numbers are so large, we're given a test statistic, by the way. We're told that it is found that in 10 weeks of birds that were sold, so it was found that in 10 weeks 95, so we're given the value of 95 there. So you need to use a normal approximation, and the normal approximation to Poisson just has the same mean and variance of 80, and I've written it like that so I don't get messed up with confusion with standard deviation and variance. Okay, so we're given a value of test statistic, as I said, of x is greater than or equal to 95, which gives us lambda equals to 8. Given that lambda equals to 8, we need a continuity correction, and I normally draw those on a number line and go back a bit. So we want the probability that x is greater than or equal to 95. If we're changing that to the continuous distribution, normal distribution, draw on a number line, how that's represented, and extend backwards. So that's 94.5. So then we just doing the standardizing stuff. So 94.5, take away the mean, divided by the standard deviation, we get this Z value. And then when we do that and fiddle around with it, this number comes from the tables, we get 0.0526, which is greater than 5%. So then we accept H1, do not reject H0. There is insufficient evidence to suggest reducing the price of Bergscope has increased demand. So that is that. You need context for this, by the way. It's very important. The mark scheme underlined the word demand. It's no good to just say accept H1 or do not reject H0. We need context at the end. Okay, so that's question 3. Let's look at question 4. Okay, question 4 is about continuous uniform distribution. Tend to draw a diagram for the first part. Part A is over here. We're told that the probability of x is less than 0.6 is that. So I've drawn it on the diagram, and then I've used that to get a ratio, because if this is 0.6 and this is 0.4, then the ratios of these two lengths has to be 0.6 to 0.4. So x minus 6 over 6 over 0.6 over 0.4 has got to be equal to each other. That's equal to 0.6 over 0.4 is 6 over 4, which is 1.5. Solving gives us alpha equals 15. Once we've done that, even easier then to work out the probability that lies between 4 and 10, because we now know the value 15 here. So again, I've used ratios rather than mess around with a PDF. The length from here to here is 6, so that's divided by 15, which is a length from 15 to 0 there. Okay. So that's part B. Part C was to find the mean and variance. The mean is pretty easy. It's just the number average in between the two. So that's 10. So you can do that by symmetry. And there's a formula for variance, so which is given in the formula book, b minus a over squared over 12. So that gives me this number here. But don't forget, it's a standard deviation we're after, so take the square root of that. Then question D, we've got a modulus thing here. The key here is to recognize the inequality, that if P is in between, if the mod of y minus 4 is less than 2, then it must lie between 6 and 2, because any between those two values, there's less than 2 away, if you like, from 4. And again, we can just look at that. That's pretty easy too, because the length from 2 to 6 is 4 over the whole lot, which is 20 in this case. So it's 4 over 20, which is 1/5. Right, now find the question C and D. I did slightly different to how the mark scheme has done it. I've used areas basically. It talks about a length that the probability of it being a square in the middle within some dot. Now I use the fact that it was equally likely to go anywhere on this screen, anywhere at all. So I just use the area, because the area of the inside is 4 times 4, and the area of the whole thing is 20 over 15, which is 4 over 75. And similarly, within 5 centimeters wide of the top of the screen, well, that means that it has to be within this red area I've highlighted here. Yeah, and remember this length here is 20, this length here is 15. So the square in the middle, because this is 5 and this is 5, and this is 5 and this is 5, has to be like that, 10 and 5. So I've used areas again. The whole area is 20 over 15. Take away, so the top is the red area basically. Take away 10 times 5 divided by the whole area, which is 20 over 5, which is 5 over 16. I pasted in the mark scheme just in case people have access to the mark scheme and said, oh, this is a different way to do it. It's fine, it's totally equivalent. But the mark scheme has used the fact that they're independent, so multiplied them out together, and you can see the numbers look very similar to what I've worked out here. Okay, so question 5 is very much question 5 is very much a it's a bit of a relief, to be honest, compared to what we've seen. There's no context here. There are some variables. It wants to find a probability that p is between 4.5 and 5.5, which is basically because it's the CDF, the cumulative function, is the same as f5.5 take away f of 4.5. The only thing is we've got some unknown variables or unknown values here of k and alpha. Well, to work out k, you might have thought that f3 is equal to 0, but it doesn't work. Basically, what we end up with is k times 0 equals 0, which is unhelpful. So that didn't work. It's true, but it didn't work. It actually occurred to me to try that, but it doesn't work. So we use f6 is equal to 1. So if we put f6 is equal to 1, we get k is 1 over 20 there. And to work out alpha, we use the fact that these two have to be equal for whatever the value of alpha is, because there can't be any, the cumulative function has to be continuous. You can't have a sudden jump in the cumulative function. It's got to go continuously. So you end up with an equation alpha, and alpha equals quite nicely equal to 5. And then once we've worked that out, we can just put the values of 5.5 and 4.5 into this function here, and we get the value 31 over 80. Okay, so then part B, really nice easy marks. We now know k and alpha, so we just have to differentiate the CDF to work out the PDF. So differentiate is what we need to do to work out the PDF. Okay, so that's that. And actually, I think I didn't get to do question 6, so I'm going to do that now. So let's quickly run this out. This is a horrible question in my view. Thank you, Edexcel. Anyway, this is my opinion. I quite like stats. I'm new to the subject, relatively speaking, but this is just fiddly and not nice. But anyway, let's do it. We've got a binomial with fair-sided dice, so there's an n number of tiles with 1 to 6. We need the mean and variance of the binomial using NP and NP 1 minus P there. And it says that a normal approximation is used, so those are the mean and variance in our, or standard deviation, square root of that, for the normal distribution which we're approximating to x. We're told that when a normal approximation is used, the answer is 0.082, so we've got to use that. So probability that the original binomial is less than 50, because an approximation is used, that means that the number using the continuity correction would be 49.5 here. Okay? Then with the 49.5, we've got 49.5, we look at 0.082, and then we do the standardizing thing. Now to work out the z value, well clearly we're looking at the left hand side tail we're given here, because it's less than and it's a small number less than 0.5. So we're looking for this z number here. Now what I used was symmetry, so basically the number I looked up in the tables was 0.9918 in order to get the z value here 2.4, because this probability here would also be 0.0082. But because we know it's negative, we know the z value is minus 2.4. Then we just got to fiddle with this, and it was fiddly, unfortunately. So at times, first of all, we've got the square root of 5n over 36 is the square root of 5n over 6. I mean, all over 36, of course. And then multiplied by that out. Then I've times by 6 to get this. And then I've times by 5 and rearranged, so I could have times by 30 in one course, of course, but times by 5 and rearranged to get this. And then we've got this unpromising looking thing here, but it's basically a disguised quadratic. if we let x be equal to the square root of n, we get this quadratic, which still doesn't look promising because it's got a square root. Bear in mind, we really want a whole number out of this. I must admit, when I was doing the question, my heart was slipping a bit. I was thinking, is this going to work out? But thankfully it did. And it just works out. I wouldn't say nicely, but it does work out. If you use the quadratic formula, you get 720 over 29700. Okay, and then that comes to 78 square root of 5. The negative one can't be relevant because that will give me a negative value of x. And then we can square so we get the value of x is 9 the square root of 5, and finally we have to square it because we let x equal to the square root of n, so that means n equals x squared, which gives us n equals 405, which is the answer. I didn't enjoy that question. It's the kind of thing that, like as I say, I quite like stats, but it's the kind of thing that if you wanted to put someone off statistics, that's the kind of question you might make up, because it really is not pleasing, in my view. But anyway, this has been a quick run through. As I say, there was a longer video for this, but it's been lost. It would take me too long to actually reproduce it. Might find it, I don't know, maybe prefer it done like this anyway, I don't know. So I hope you found it useful. Bye.